we'll go from current slide. And sorry we're 6 minutes late getting started, but we only have one student in the room. We had two, but that was a leftover from the last class. Our volleyball women, I guess their season's over. I haven't heard how they did in the tournament, but hopefully they did well. I think they did, but I don't know for sure. And then the only other thing is the thing from the postdoc at UAB in microbiology or somewhere like that. And she came across this 1 week summer opportunity for college students interested in biopharma manufacturing careers. And 1 week, the students are paid $1,000 and travel expenses are covered. The application deadline is sometime in January. That's all the information I have except for the website. And if you want to see it, there it is. All right. So hopefully more students will be coming in, but since they're not here now, let's go on and get started. This is the last section in Chapter 8, which is integration techniques and improper integrals. This is the improper integral part, okay? And since they're not proper, let's not do it. No, you're not going to be tested on this. You already got your test. I don't believe there were any improper integrals on it, right? Yeah. So the objectives here are evaluate an improper integral that has an infinite limit of integration. And then we'll also evaluate improper integral that has an infinite discontinuity. So there's two types of these improper integrals. One, you're integrating to infinity, which, how do you do that? And the other one, you're integrating something that has an infinite discontinuity in it. How do you do that? Well, that's what we'll be looking at. And let's start with improper integrals with infinite limits of integration. All right. The definition of a definite integral is like this. The integral from a to b, f of x dx. It requires an interval, a to b, which is finite. There is some endpoint on the left and some endpoint on the right, and that's a finite interval, and you either can or can't do the integration. Furthermore, the fundamental theorem of calculus requires that f be continuous in that interval, a to b. We'll study a procedure for evaluating integrals that do not satisfy those two requirements, usually because either one or both of the limits of integration are infinite, either this one, that one, or both, okay? Or because f has a finite number of infinite discontinuities in the interval from a to b. In other words, you can't have an infinite number of discontinuities there. That would be impossible. But if it had a finite number that you can deal with, and that's the issue. Can you deal with them? And we'll see this. Integrals that possess either property are called improper integrals. Improper because of their limits, or improper because of their discontinuities. Note that a function f is said to have an infinite discontinuity at c. This is the thing we're doing second. We're supposed to be doing infinite limits first. We'll talk about this one first. Discontinuity at c when from the left or from the right or from the left, the limit as x approaches c of f of x is dx. In other words, f of x is going to either a positive or a negative infinity as x approaches c, either from the left or from the right. Okay? To get an idea how to evaluate an improper integral, this has almost nothing to do with this. Okay? But anyway, it has a little something. No. Yeah, it does. Okay. To get an idea how to evaluate an improper integral, okay? This is either kind. That's what my board here, didn't I? Okay. Consider this integral. The integral from 1 to b of dx over x squared. Okay? Now, as long as b is any number greater than 1, okay, we can do that. Okay? All right. We've just doubled the class size. Maya's here. Okay, middle part of the alphabet's doing quite well here. And you did get a quiz test last time, didn't you? Yeah. All right. If you integrate this, I would have written it as x to the minus 2 dx. That would be minus 1 over x. Okay, there it is. Then you can evaluate it first at b, minus 1 over b. B, of course, being a number greater than 1, plus minus a minus, which is plus 1 over 1, which is 1. So this will be 1 minus 1 over b. Okay. Now, with that in mind, that's perfectly fine. No problem there. We can do that, as long as b is finite. But what if b is infinite? It's going to infinity. What's that going to? 0. So we do have a value. Even if this this graph, 1 over x squared, it comes out pretty quickly and then tails off going to infinity, no matter if you went to infinity. If you did go to infinity, it's just a hair less than 1, but even if you went to infinity, it would be exactly 1. Can't go to infinity, but that is the limit, would be 1. So we can say, we can evaluate that as b approaches infinity and give us a value. It's a limit, but it will give you a value. That integral can be interpreted as the area of the shaded portion here. Here's the function, f of x equal 1 over x squared. Now, as long as you're evaluating this from 1 to somewhere here, okay, somewhere out there, you can do that evaluation. Because this is approaching 0 so quickly that any value out here, just like we saw, any value b would just be a little bit less than 1. I mean, b is a lot less than 1, but your total integral would be a little bit less than 1. And if it was going to be, if b was going to infinity, then the b would go to 0. But that would, the unbounded region has an area of 1. Take the limit as b approaches infinity. Do it just like we said. The integral from this to that is the limit as b approaches infinity, the integral from 1 to b, dx over x squared, which we just calculated, and that was 1 minus b. Then you can take the limit of that as b approaches infinity, and that comes out exactly 1. So, anything less than infinity here is going to be a number awfully close to 1, but not quite. So when it goes all the way to infinity, whatever that is, then it would be exactly equal to 1. That improper integral can be interpreted as the area of the unbounded region of the graph, f of x equal 1 over x squared, and the x-axis. That's, of course, anything to the right of 1. Now, as you might guess, you could have made it from 1/2, or 1/10, or 1/1000. You could have done it from anywhere. Of course, those are getting quite bigger, okay, because this has a limit 1, do 1/2, and you're going way more than double that size, and the further you go. But this is the second time. This has a discontinuity as x approaches 0. That one, I'll just tell you right now, would not have a limit. We're going to get to that later, but that one would not. So as long as you're anywhere on the right-hand side of 0, anywhere on the right-hand side of 0, you can evaluate this one as that goes to infinity. Okay. Now, if you did the entire graph for negative x's as well, that would just be over here. Because this is still a positive value, it would just mirror this. That would be an even function, just mirroring that. You could go from negative infinity to any point short of 0. Can't get it to 0. You get to 0, not defined. Okay? But anywhere else would be, you could do that. But you can never cross 0. The limits here can't go from -1 to 1. Not going to happen, okay? But from 1 to anywhere that way, from negative infinity to anything short of 0, that would be fine. Okay, because that's what it represents. So here's the definition of improper integrals with infinite integration limits. The first case. If f is continuous on the interval from a to infinity. Of course, infinity is not a number, so we can't block it in, okay? That's always followed by, or if it's negative infinity, preceded by a parenthesis. If it's continuous throughout the interval from a to infinity, then the integral from a to infinity of f of x dx is the limit as b approaches infinity of a to b of the f of x dx. Is it guaranteed to have a limit? No. So this is not guaranteed to be an actual integrable function. Okay? It's only if that has that limit, if b approaches infinity, like the last one. Now, if f is continuous over an interval from negative infinity to some quantity b, now remember it has to be continuous here. We can't have a discontinuity like we did on that last one. From negative infinity to b, then the integral from negative infinity to b of f of x dx would be, just like before, the limit as a approaches negative infinity of a to b f of x dx. That's a definite integral. If you can evaluate that integral, fine. But then if that value has a limit as a approaches negative infinity, then that's how we define our improper integral here. Now, if f is continuous on the interval from minus infinity to positive infinity, then we can still write this, the integral from negative infinity to infinity of f of x dx, okay, of negative infinity to c, f of x dx, plus the integral from c to positive infinity of f of x dx, where c is any real number in between, of course, negative infinity and positive infinity, and then you do this one like this one, and you do this one like that, okay? And you do that. Now, they both have to have a limit for this to work. If either one of them doesn't, you can't do the whole thing. In the first two cases, the improper integral converges when the limit exists, there or there, okay? Otherwise, the improper integral diverges. It has no value, okay? In the third case, the improper integral on the left diverges. In the third case, the improper integral on the left diverges when either of the, this one, okay. When either of the improper integrals on the right diverges. So in this case, both this one and that one would have to converge. And if they did, then that would converge as well. All right. Now, since you're not going to be tested on it, well, this is something you could be tested on because it's not an improper integral, is it? So let's do that. What does it give us? Anybody? That's log of x. Natural log of x evaluated from 1 to b. And what would that be? Log of b minus, what did you say? 0, exactly. Log 1 is 0. So, there's your answer. Could b approach infinity? It could, but this interval wouldn't be defined because this does not converge. Log b just keeps climbing and climbing and climbing, so there is no limit. So for any finite b, this has a value. But for an infinite b, no. So this one would not be would not converge, I guess is the best way to say it. Okay? All right. Now, the thing is, this problem's just sort of backwards. I think what they wanted to have was the infinity up there at the top, said evaluate that, then you would come down here and do that. But you see, the problem wasn't evaluate from 1 to infinity. It was 1 to b. 1 to b has a limit, okay? It's only when b approaches infinity does it not have a limit, okay? Now, and they show you the graph there, okay? Now again, I only did that because that wasn't an improper integral. They made it into 1, but it wasn't 1. So if that was the original problem, this one doesn't exist because that's what you get to, and as b goes to infinity, that has no limit, okay? All right. Now, I really don't like it for them to say the answer is infinity. That's not a number. To me, you say this one does not exist. Maybe there's some esoteric reason that should, but it doesn't. Okay. Now, the limit does not exist. That's what they should have said. So you can conclude the improper integral diverges. It does. And whereas the other graph looked a lot like this one pains and approaches 0 much, much, much more slowly. So it never, it doesn't have a limit. The other one, this was its result of the integral. This is what you're integrating, and with the log x, that's always increasing. The unbounded region has an infinite area. You can't look at these and tell. You have to do the limits. Now, they skip example 2, which we'll skip to, example 3, which we'll skip to, example 4. Now, if you think you may run into this and need it some ways, yeah, you might want to go back a look. Even example 5, they skip that one as well. So, don't know which way you're heading with math, but if you need this, maybe pay a little more attention to them. You're a pre-engineer? Huh? Oh, computer science. I doubt if you're going to be approaching infinity anywhere, are you? Okay. It may seem like you are with all the bits and whatever, but no. So let's move on to improper integrals with infinite discontinuities. Okay? Now, that doesn't mean an infinite number of discontinuities. It means discontinuities that go to infinity. Okay? Here's a second basic type of improper integrals. Is one that has an infinite discontinuity at or between the limits of integration. Okay? And infinite discontinuity. We're talking about 1 right now. Later we'll extend this to some finite number. But here's the definition of improper integrals with infinite discontinuity. If f is continuous on the interval from a to b, notice b has a parenthesis after it, so it's continuous at a, defined at a, but not necessarily defined at b. So we leave that with the parenthesis. And has a discontinuity at b. So yeah, it wasn't continuous then, there's a discontinuity there. Then what we do is take the integral from a to b, just like we normally would of f of x dx, because f is continuous up to b, and then we take the limit as c approaches b from the left-hand side, from the negative side, and do the limit as of the integral from a to c, f of x dx, and figure out what that integral is, and then take the limit as c approaches b from the negative side. If f is continuous on the interval a to b, this time a is not included. B is included, has an infinite discontinuity at A, then we go and do the integral from A to B like we normally would of f of x dx. That would be defined as the limit as C approaches A from the positive side now. You're coming in from this side, and do the limit of C to be f of x dx. See if you can evaluate that one, and then take the limit as C approaches A from the right. Now, if C is continuous on the interval A to B, except for some one value C somewhere inside A to B, at which f has an infinite discontinuity, then this integral here, if you can do it, would be the integral from A to C, f of x dx, plus C to B, f of x dx. Well, A to C would be exactly this one, and C to B would be exactly that one. So you do the limits as you integrate this function from A to C, and then let C approach B from the left. Evaluate this one, let C approach B from C approach A from the right. I'm sorry. Saying that. Yeah, that's right. Evaluate this one, let C approach B from the left, and here C approach A from the right. Seems like they have these backwards. Yeah, I guess that's right. In the first two cases, the improper integral converges when the limit exists. Otherwise, the improper integral diverges, so it doesn't have an integral. It doesn't have a value. In the third case, the improper integral on the left, this one, diverges when either of these diverges, so they would both have to converge for that to have a limit, for that to have a value. Okay. Now, is anything wrong with that picture? Evaluate the integral from 0 to 1 of dx over the cube root of x. Again, let's write it slightly differently. What would that be?
Would be x minus 1/3.
Right, dx. Now, actually, it's probably easier to see what the problem is on the left, but to do the integration, we're going to need it like to the right. What's the problem?
0 can't be.
You can't divide by 0, so that doesn't look like it makes any sense whatsoever. But what we'll do is then, I don't want to get into this. Well, let's get into it. What would, if we'll change this to be the integral from, you want to call it A to 1 of x to the minus 1/3 dx, where A is some number, some small positive number. Okay? What would this integral be?
X to the 2/3.
2/3.
Times
3 over 2, okay. Divided by 2/3 or multiplied by 3/2. And we'll evaluate that from, well, I should have written this in. The limit as A approaches 0 from the right-hand side, okay? You're going back towards 0. So this will be the limit as A approaches 0 from the right-hand side. And this will be from A to 1. And I think if I plug in a 1, I can probably do that. What would that be? 3 halves minus 3 times the a to the 2/3 power over 2. Now, whoops. You can tell I have a Freudian thing about limits. You know, I just really don't like them that much. But this would be the limit as a approaches 0 from the right-hand side. That's what that would be equal to. And what is that? Yep, it'll just be 3 halves because that one will go to 0. Yep. So that one does have a limit. I said we weren't going to do any of these, but thought we would do the integral just to review the integral there. Okay, so that was example 6. And that one does have a limit, and its limit is 3 halves. Okay. Let me erase my scratch here. I'll let you see what they do. The integrand has an infinite discontinuity at x equals 0, shown here. And since you're only going to 1, but again, and there's no way to tell this by looking, so don't even try, but again, this is approaching 0, approaching as x approaches 0 here, this is getting really, really, really close to the y-axis, so there's very little area being added here. And as you do that, as x approaches 0, it's such a small amount that has a finite limit there. If you remember, we had 3 halves minus a quantity here, and that quantity kept getting smaller and smaller and smaller as x was approaching 0. So small that it disappears by the time it reaches infinity. If it didn't disappear, then this would diverge, and it wouldn't have a limit. Okay? But you can't tell by looking. Okay? Don't worry, you can't. You can evaluate that integral, as we said. They write it a different way, but it's still okay. They use B down there rather than A. I don't know why, but it's okay. And that limit would be, as B approaches 0, would be 0. So that'd be 3 halves. So that leads to theorem 8.7, a special type of improper integral. Okay? If you have noticed, the first example was a dx over x squared. The second example was a dx over x. Okay? So this is going to summarize what we were seeing there. The integral from 1 to infinity, when you've got a dx over x to the p, okay, if the p is a number greater than 1, this will always converge to this. Remember, we had a 2 here. 1 over 2 minus 1 is 1. 1 over 1 is 1. That was exactly what that limit was. But when this p was a 1, when it was dx over x, this would be 0. So this one would not work there. It diverges. For any p1 or less, okay, any p1 or less, that diverges. Okay? Special rule for those. Okay. And here's example 11, the solid formed by revolving about the x-axis. The unbounded region lying between the graph of f of x equal 1 over x and the x-axis, this is for any x greater than or equal to 1. It's called Gabriel's horn. Gabriel must be over at infinity somewhere, okay? Blowing his horn back toward the negative side. And it says, show that this solid has a finite volume, but an infinite surface area, which is rather interesting. Finite volume, but infinite surface area. Well, infinite surface area because 1 over x, that didn't fit the bill in the last thing, so if that was infinite, when you revolve that around, that certainly will. The volume part is the interesting part. I'll just walk you through that. Using the disk method and theorem 8.7, you can determine the volume to be, the disk would be pi r squared, and this is going from 1 to infinity. Yeah, you're starting at x equal 1. They never quite said that. They just said that would be there. So then it would be the volume would be all those areas, you know, summed together, which is the volume here. Pi times 1 over x squared, pi r squared. Your radius here was your x value. Pick a little delta x here. Okay, here's the thing you're revolving around. Okay, doing this around there. Your radius of that circle of revolution here, the radius of that would be 1 over x, and since it's pi r squared, that would be the area of that circle. Okay, then this is your a squared, so pi's, okay, pi 1 over x squared dx. Well, that's the first one we had. That would be pi times, remember that, 1 over x squared, 2 minus 1 is exactly that, would just be 1. That would have a volume of pi, okay? Perfectly fine, okay? But the surface area, on the other hand, is 2 pi times, remember how we did the surface area? 2 pi r, okay? And then you do the arc length, which is the square root of 1 plus f prime squared, okay? Your f prime here would be minus 1 over x squared, right? And then you square that, you get 1 over x to the 4th. So you have a 1 over x here multiplied by something a little bit greater than 1 over x. Hey, if this is infinite, then that will certainly be infinite as well, because it's something even greater than that. So no, the surface area is infinite, because that thing there is greater than 1. For all values x greater than 1, that's greater than 1, just a little bit. And on the interval from 1 to infinity, the improper integral then would be this improper integral diverges. Okay, I couldn't see the word here. Diverges. You can conclude that since you're multiplying something that diverges with something greater than 1, it also diverges. That really used a different rule that we haven't really discussed, but it obviously is true. Okay. So the surface area is infinite, even though it has a finite volume, which is bizarre. Now, do any of those you desire to do. You're not required to do any of them. It's only if you want to have some practice doing those. Now, review exercises may be another fun thing besides Ryan coming in to do, especially if you run into some exercises on your test. Did you get a copy of your test?
I did.
Okay, good. Then the review exercises, the odd answers are at calcchat.com, and 1 through 7 would be possibilities, odds 9 through 15, all at CalcChat. 17 through 25, all at CalcChat. The first group, basic integration rules. The second group, integration by parts. This group, 17 to 25, trigonometric integrals. 27 is another trigonometric integral. It's just a little bit different one, okay? Then trig substitution would be any of the odds 29 to 33, all at CalcChat. then using different methods, that's pretty specific, isn't it? That would be 35. Partial fractions, 37 to 43. Trapezoid rule and Simpson's rule, 45 or 47. Integration by tables, 49 to 55. And then the indefinite integrals, I think those are probably using tables or a combination of things that you would need there. 57 to 63, all at Calc Chat. They do a couple of differential equations, even though it's a different course. You can look at those if you'd like, 65 or 67. And then some more definite integrals, 69 to 73. And then it says any method you want, 75. 77 is a centroid problem. You have to go back and review that. The evaluating improper integrals from 79 on, you don't have to do that. Okay. You can probably do the first part of 87 if you'd like. And the others are infinite improper integrals, so you don't have to mess with that. I would bring your attention to number 89, probability, which is something you're going, especially if you're a math major, you're probably going to see. So you might want to take a look at 89. Then there's a little section on problem solving. They go back to Wallace's formula, which we talked about before, and some other things. You're certainly welcome to do any of those odds that you'd like. The odds have answers at calcchat.com. You don't have to do anything. But let's move on to Chapter 9. Now, Chapter 9, let me just tell you how things are going now, okay? Chapter 9, we're only doing 9.1 and 9.2. If you go back to your course description in the syllabus, it said sequences in series. Now, sure, there's more in here. There are 10 sections in here. We don't have time for them all. We'll try to do, like I just did in that last one, a quick slideshow. It may not have seemed too quick, but a slideshow of the 9.3 to 9.10, but you're only responsible for 9.1 and 9.2. Okay, so that's what we're going to launch into now. Then we'll do a slideshow on the rest of them. This is one long chapter. We could spend basically the rest of the term on this chapter. We really need to get to other things, so at some point here, I will get to the end of the chapter. Here we go. Then we'll go to chapter 10. Now, there was nothing in your course description that said anything about 10.1, conics and calculus. You can look at that if you're interested, but that's it. We'll do 10.2. I'll do a slideshow on 10.1. But you're responsible for 10.2, plane curves and parametric equations, 10.3, parametric equations in calculus, and 10.4, polar coordinates and polar graphs. We probably won't do as much with polar graphs, just polar coordinates. Okay? You may do a quick slideshow of 10.5 and 10.6, but that's all. Okay? Now, so we'll do 9.1 and 9.2, 10.2, 10.3, and 10.4, and then, and again, 10.3 we could spend basically almost the whole term on. We will go to chapter 11, and we will go as far as we can in 11. 11.1 through 11.5. We're not going to do 11.6. That's the beginning of Cal 3. So we'll do as much as we can, 11.1 through 11.5. We'll probably run out of term before we get all of 11.5 done, but as far as 11.5, so the last test, your final exam, will be 9.1, 9.2, 10.2, 3, and 4, and then anything we can cover from 11.1 through 11.5, as much as we can cover in that, and then that'll determine your final. Okay? Because I don't think we're going to have time to finish all that, but we'll get as much done as we can. So let's get started in Chapter 9. Infinite Series is the title of it. Okay? We'll start with sequences. Okay? The objectives here are to write the terms of a sequence. The individual terms of a sequence. We've got to first figure out what a sequence is. Then we'll determine whether that sequence converges or diverges. Sort of the same type of thing we were doing with infinite integrals. Okay? Or improper integrals. We'll write a formula for the term of a sequence when that's appropriate. And we'll use properties of monotonic sequences and bounded sequences. Okay? Again, some definitions will be in order. So let's start with sequences in general. A sequence is defined as a function, okay, you may not think of it as, whose domain is a set of positive integers, okay? Rather strange, huh? Although a sequence is a function, it is common to represent sequences by subscript notation rather than the standard function notation. So here's an example. Here is a sequence. This sequence is actually your positive integers. 1, 2, 3, 4, 5. The domain is that. Well, no, I'm sorry. This is the domain here. Here's a sequence. 1 maps onto ace of 1. 2 maps onto ace of 2. 3 maps onto ace of 3. 4 maps onto ace of 4. All the way up to n mapping on ace of n. Okay? That's not very descriptive, is it? We don't know anything about the a's. One is, okay, this is saying the same thing I just said. The numbers A1, A2, A3, A all the way up to A to N, and O are terms of the sequence. These are called the terms of the sequence. The number A sub n represents the nth term of that sequence. And that is how we usually refer to a sequence, by its nth term. Okay? The entire sequence is then denoted by the set of all these n terms. Okay? All the ones up through a sub n. Well, and beyond, if you keep on going beyond. That's how we refer to a sequence. So, they're going to give us the definition of the operation, basically the function of the sequence. A sub n, where n are positive integers, okay, is the set of 3 plus -1 to the n. Okay? Now, I hate they've already started doing it for you, but let's just take it. We'll start with n equal 1. Okay? Let me get my pen set up. Okay. 1 is going to map into what's a sub 1? Tell me. 3 plus -1, which is 2. It's 2. A sub 2 would map onto a 3. I'm sorry, plus a -1 squared, which would be 4. 3 would map onto 3 plus -1 to the third power, which would be 2. 4 would map onto 3 plus, it's what? negative 1 to the 4th power, which would be 4. Any guesses on what would follow that? 2, 4, 2, 4, 2, 4, 2, blah, 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 dot, dot, dot. Okay, it goes on forever that way. This is a sequence. 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. Okay, that's it. Okay? Now, that is the definition of your nth term. That describes everything you need to know about the sequence. We've actually evaluated it for several, and we quit evaluating because we saw the pattern. And most sequences will have a pattern. Whether you can see the pattern, that may be a different issue, but they will have some sort of pattern. All right? Now, I don't know what more we can do with that one. Yeah, that's just 2, 4, 2, 4, 2, 4, 2, 4. That's the A one. Okay? Let me erase my scratch. And there they give it to you. 2, 4, 2, 4, 2, 4, and so on. Dot, dot, dot. Usually they just put 3 dots, but they put 4. That's okay. Now the B one. Here's B. B sub n, you can name the name of the term anything you want to, is n over 1 minus 2 to the n. Okay? I wish they hadn't have done this, so let's just pretend they had. Okay? What would be 1 maps onto, what would be b to the 1? B sub 1, I'm sorry. 1 over 1 minus 2, which would be negative 1. 2 would map onto 2 over 1 minus 4. Is that what you said? Which would be negative 2/3. 3 would map onto 1 minus 6, which would be 3/5, negative 3/5. 4 would map onto 4 over negative 4/7. Okay? I want to make a guess about the next one would be? Negative 5/9. The next one would be? Negative 6/11. Okay, you see the pattern here. Okay? Your numerator is going up by 1. Your denominator is going up by 2, but it's always, the fraction is going to be negative, always. Does it look like, okay, we didn't say it. Let's look at this first one again. Does that look like it's going to converge anywhere? Does this get closer and closer to any value? No, it's just back and forth, to 2 to 4, to 2 to 4, to 2 to 4, to 2 to 4, not ever getting closer to anything. What's this one doing? It is getting smaller. Starts at negative 1, goes to negative 2/3, to negative 3/5, negative 5/9, negative 6/11. Is it going to 0, you think? Okay.
Yeah, I think so.
All right. Okay, the next one would be negative 7/13. Next one?
8/15.
Negative 8/15. Okay. Well, notice, let's just do some decimal. That's negative 1. This is negative 0.66662. This is negative 0.6. This is negative, calculator. But this is still greater than 1/2, isn't it? I mean, the absolute value. It'd be 3.5 over 7 would be 1/2, right? This would be 4.5 over 9, 5.5 over 11. In other words, if this were an 8, or let's do that this way. If the denominator here would have been a 2, that would have been a minus 1/2. If it would have been a 4, that would have been a minus 1/2. A 6, that would have been a minus 1/2. An 8, that would have been a minus 1/2. But they're not quite. So guess where this one's going? Closer and closer to negative 1/2. Right? Because this, none of them will ever get to 1/2, but they get closer and closer and closer. So this actually is, that was beyond where we're going now, but that's, I think, yeah, okay. So let's us erase this, and they did the first 4 there, and they got that to -1, -2/3, -3/5, -4/7, -5 ninths, -6 11ths, -7 13ths, you know, and on and on and on. Okay. Now, here's another one. Let's pretend they didn't show us that. Okay. The C one here. C sub n is that. Let's do 1 mapping onto what? One over, which is 1. Okay. 2 maps onto what? 4 over 3. Okay. 3 maps onto 7. 4 maps onto 16. Okay. 5 maps onto what? 31, isn't it?
Yeah.
Yeah. Okay. 6 maps onto right? Okay. Now, if you stop too soon, this is 1, this is 1 1/3, this is 1 2/7, this is 1 1/15. See, increasing here, but then they start decreasing. So at first it looked like it was going to converge, then it looked like it might go back to 1, but then it goes less than 1, and even less and less. Where do you reckon that was heading? Hard to say, and we're not, you shouldn't know it yet. But 2 to the n increases much more rapidly than n squared. 2 to the n is an exponential increase, n squared is a quadratic increase. Quadratic increase follows a parabolic form, exponential increase really takes off and goes. Even though to begin with it's less, but after a while the denominator takes over. My guess this one's going to 0. Doesn't look like it now, but I think it is. Okay? We can see later, but we'll maybe not. We'll see. Okay. Now, let's clear this and let's see what they got, make sure I didn't do something wrong. They're not saying anything about what goes on here. They just stop at 16/15ths, and that's sort of not the best place to stop, because they do start getting, well, you can see the trend was up and now down, and it continues to go down. Now, there is another kind of a sequence that's a little bit worse. This isn't just an A sub n or D sub n or something like that. You define the next one by what the previous one was. Okay? So this is a recursively defined sequence, D sub n. It is a D sub n, but you don't have a formula for D sub n. You have D sub n is equal to something related to what D sub n minus 1 was. So D1 is 25. D sub n plus 1 is D sub n minus 5. Okay? So what would be, I hate they do this. They don't give us much room to do this. So we got 1 mapping onto 25. They told us what that was. 2 would map onto D sub 1 minus 5, which would be 20. 3 would map onto 15. 4 would map onto 10. 5 would map onto 6 would map onto 0. 7 would map onto negative 5. Okay? Certainly a decreasing sequence, right? You think this has a limit? Keep on going. 25, 20, 15, 10, 5, 0, negative 5, negative 10, negative 15, negative 20, going to negative infinity. Not anywhere close, and we're not doing that yet, but just to let you know, that's what it was. They stopped at the fourth one, which was 10. Okay. Now let's talk about the limit of a sequence. The primary focus of this chapter, first 2 sections especially, concerns sequences. Okay, I don't know, that sort of bothers me. The chapter is going to be talking mostly about series, okay? But series are made up of sums of sequences. But concerns sequences whose terms approach limiting values. Subsequences are said to converge. Okay? Some of these do. Here's one. 1/2, 1/4, 1/8, 1/16, 1/32. What's the sequence here? What would be your nth term here? 1/2 to the first, 1/2 to the second, 1/2 to the third, 1/2 to the fourth, 2 to the fifth, the 1/2 to the nth term in that would be that. Does it look like it's converging? Getting less and less and less, but never going on to negative. Huh?
It's getting closer to 0.
It's getting closer to 0. Will never reach 0, but it'll never go beyond 0 either. Okay, you can read that, can't you? Okay, convergence to 0 is indicated in the following definition. Let L be a real number, any real number. The limit of a sequence, A sub n, is L, written as this. Limit as n goes to infinity of A sub n is L. If for every epsilon, this sounds like a good old limit again. If for h epsilon greater than 0, there exists now, it's not a delta, but some capital M, also greater than 0, such that if the absolute value of A sub n minus L, if that is always less than epsilon, whenever n is greater than this capital M. Okay? If you can get your n's big enough, and if you can get the difference between these two to be less than epsilon for every n beyond this m here, then the limit exists. If the limit L of the sequence exists, then the sequence converges to that L. If the limit of a sequence does not exist, then the sequence diverges. Okay. Now, don't pay too much attention to my hand. I said diverges. It doesn't always diverge mean like this. It may be like this in divergence. It doesn't have to be getting further apart. It just cannot be converging. Okay.
So what is epsilon? Should we know what that is?
What's that?
The epsilon, what is that?
Okay. Let's just take an example here. You pick a small number greater than 0. As small as you want it to be. Say again? 0.2, is that what you said? 0.1. Okay, say your epsilon is 0.1. Well, if this has a limit, then for every m, there exists some value m out there that for every n beyond that m, you're guaranteed that the difference of a sub n and L is going to be less than that 0.1. Every one. None of them get outside past that. And you can pick even smaller, and you can just go far enough, and it always is going to be. Okay? So that's what it is. It's a lot like what we had with derivatives and stuff. Your epsilon is some interval of your y, you might say. The delta would be some interval of your x. But what we're saying now, any n beyond m goes somewhere out here. For instance, that one that we did before, where it started off increasing, but then started decreasing. During that increasing range, it doesn't seem to be converging. It seems to be getting bigger. But then it seems to come down and maybe converging to 1, but it keeps getting less and less. And I said, I think it's going to 0. Couldn't tell by just the number we did. But if you picked an epsilon and say you want it as small as possible, if you could find some capital M somewhere out there that for every n beyond m you guarantee the difference between this and that is less than the epsilon. No matter how small you get, then yeah, it converges, and if that's the case, your limit is L. If you can't find that, then it diverges. Okay. Even though you said L is that real number, if you can't find one that a sub n is always within epsilon units of it, then it diverges. Graphically, this definition says that for some n greater than m, and epsilon greater than 0, the terms of a sequence that converges to L will lie within a band that's within, again, epsilon is the difference. Here's your L. Here's L plus epsilon, L minus epsilon. You can get epsilon as small as you want, and it said that after a while, every point is going to have to guarantee to be within the limit. It fails here, but that doesn't matter. If you can get some n big enough, then that m would be, from this point on, it looks like all of them are going to fall within that. Because this is doing something like this. Somewhere out here, it's staying within that limit, within that bound. So yeah, the limit does exist. Okay. And for any epsilon you choose, no matter how small, get it on out here, somewhere way out here, and you got them, they're staying in between that, the limit exists. Okay. Does that kind of make sense? Does that kind of answer your question? Okay. Good question, by the way. So here's theorem 9.1, the limit of a sequence. Let L be a real number, any real number, then let F be a function of a real variable such that the limit as x approaches infinity of f of x is going to be equal to the L. did we get there? Well, remember, a sequence is a function. It's just now your argument here are only positive integers. Okay? So if a sub n is a sequence such that the f of n is equal to a sub n, that's what it is. That's how you define it. For every positive value n, positive integer n, then the limit as n approaches infinity of a sub n would be L. Seems like they're going in a complete circle here. What's that? Yeah. But I'm sure what they're saying is right. It just is a kind of a weird way to express it. F be a function of a real variable such that this is how you define the L. Oh, as that goes to infinity. Okay, got it. Yeah, that's right. Then, if a sub n is a sequence such that this f of n is equal to your a sub n, if this defines your nth term there, and this limit exists, then the sequence also exists. That's what they're saying. Okay. If f is a function such that it converges as x goes to infinity, if a sub n is a sequence such that alpha of n, where n now is, this is any value x, okay? Any value x, all real numbers x here. But if this works, and that has a limit, then f sub n, when n is just your positive integers, equal to a sub n for every possible positive value n, then this one will also converge, and it'll converge to the same thing. Okay. All right. So, find the limit of the sequence whose nth term is this. Okay? Now, some of you may recognize this, and if you do, it's probably going to hinder your ability to see what they were just talking about. But let's see if we can do it. Now, what you have to do then is see if you can find a function f of x, and you're just going to substitute everywhere you see an n here, you put an x. 1 plus 1 over x raised to the x power. Okay. And they really cheat here. Okay. Because they refer you back to an example in a section term ago, okay, sometime a long time ago, that you actually did that. But let's try plugging a few numbers in, okay, and you'll need a calculator. So let's plug in the number 1. 1 plus 1 over 1, that would be 1 plus 1 is 2. 2 raised to the first power is 2. So a sub 2 is equal to 2. A sub 3 would be equal to, no, a sub 1 is 2, sorry, I forgot. A sub 1 is 2. A sub 2 is 1 plus 1/2, that's 1.5 raised to the second. That's 2.25, isn't it? Okay. A sub 3 would be 1, let me just write as 4/3 raised to the third power. 2.27, is that what you said? 37, is that what you said? Okay. A sub 4 would be 5/4 raised to the 4th power, right?
2.44.
2.44. A sub 5 would be 6/5 to the 5th, right? 2.49. Okay. A sub 6 is 7/6. I think I'm doing this right? Yeah. Raised to the 6th. 2.52. A sub 7 is 8/7 raised to the 7th power. 2.55. Okay, here's the deal, folks. We're going up. That one went up by 0.25. That went up by 0.08, 07, 05, 03, 03. So it's going up, but the amount that's going up is getting smaller and smaller. So let's just jump somewhere like A to the A sub 10 would be 11/10 raised to the 10th power. 2.5 what?
9.
5.9? Oh yeah, right, it's going up still. Okay. How about A? I don't know how far your calculator will do. This would be 21/20 raised to the 20th. Will you do that?
2.65.
See, 2.65. Let's try A. I don't know if your calculator will do this one. To the 100th. That would be 101/100 raised to the 100th power. I don't know if your calculator will do that, will it?
2.70.
2.70. Didn't go very far that time, did it? I don't know how far your calculator will go. Let's try 200. 201/200 raised to the 200th.
2.71.
2.71. Is that sure isn't increasing much, is it? Okay. Do you want to try a few more? Will your calculator do 300?
I think so.
A to the 300 equals 301/300 to the 300th. Some point your calculator won't do exponents anyway. 2.71 again. Now, what is 2.71? Does that ring a bell?
It's close to E, isn't it?
It is E. I mean, yeah, you're getting closer and closer to E. So this limit is E. F of x as x goes to infinity is E. So A sub n, this limit is also E. Absolutely right. They based on what you remembered from example 5 in section 5.6, which was a long time ago. Okay. Now,
So is that just the answer?
your answer is E, because the function's going to E, so the sequence goes to E. And they just said, based on what you learned before, this is what they do. You learn that. Yeah, right, I remember that. Well, I do, but I don't know that you would. Did you remember that looking at it? That's how you define E, okay? So you can apply theorem 9.1 to conclude the limit as n approaches infinity of A sub n is also the limit as n approaches infinity of this thing, which we were just doing, and that is approaching. It took us a long time to get there. I mean, to begin with, it seemed like it was going there incredibly slowly, and I never would have, without knowing it, guessed that was going to E. But after a while, and you got a big enough n in there, and your calculator can handle it, you see it is going closer and closer to E. So there are different ways in which a sequence can fail to have a limit. Okay? All right. One way is that the terms of the sequence increase without bound, or decrease without bound. Remember that one? That was minus 5, minus 10, minus 15, minus 20. Yeah, decreasing without bound, that one is not going to have a limit. Or those that increase without bound, just 1, 2, 3, 4, 5, 6, 7. If they mapped onto themselves, that's not going to have a limit. So there's one way. Terms of the sequence increase without bound or decrease without bound. These cases are written symbolically, as shown below. Terms that increase without bound, the oh boy, yeah, this is pretty. Limit is n approaches infinity of a sub n. It's positive infinity. This is negative infinity. Okay, I'm glad they showed us that. Rather than saying this, rather than expressing it like that, I say does not exist. The limit as n approaches infinity does not exist. To say it's equal to something indicates there is something. There's not. It doesn't exist. Okay. But I guess there are reasons that would be somewhat advantageous. So, stop right there and say, here's theorem 9.2. Properties of limits of sequences. Let the limit as n approaches infinity of a sub n equal L, and the limit as n approaches infinity of b sub n equal K. So you're telling us this one has a limit, that one has a limit. This is the limit for A, this is the limit for B. Okay? Scalar multiplication. If you have the limit as n approaches infinity of c times a sub n, that's just going to be pull the c outside the limit. That would leave you L, then multiply CF for any real number C. As big as you want C to be or as small as you want C to be, and it'll be it. Some are a difference. The limit is n approaches infinity of a sub n plus or minus b sub n would then be L plus or minus K. You can take the limit. The sequences are basically linear in nature. Product. The limit as n approaches infinity of a sub n b sub n is L times K. All this hopefully is making perfect. You say, okay, that makes sense. Okay. The quotient. The limit is n approaches infinity of a sub n divided by b sub n is L over K as long as your b sub n is never a 0 and your K is not equal to 0. That would rule out the quotient. But all the others would be just what you would expect. Okay. All right. They are skipping examples 3 and 4. So let's go back and do examples 3 and 4. Okay. All right. Looks like this is going to be about the most amount of white space we're going to get here. By the way, example 3, you can see larsoncalculus.com for an interactive version of this type of example. Now, does it seem like to you I'm harping on this too much? LarsonCalculus.com, CalcChat.com, CalcView.com. Are y'all getting sick and tired of it? Probably, but it doesn't matter. I'm still going to do it. And here's why. I had a student come in for advising last week. I can't remember which day it was, Wednesday, Thursday, sometime last week. And he was talking about having some problems with his trig class, you know, but he was managing through it and stuff, and asked if I had any advice or something and stuff. I said, well, are you going to calcchat.com? He said, what? I said, I had the book there. And that was pre-calculus, not calculus. I said, look here, okay, back of the book, LarsonPrecalculus.com, CalcChat, CalcView. He had never heard of any of the three. And he had been in 112 and now was more than halfway through 113 and never had heard that these things even existed. Now, I don't know what he did reading his book, just completely ignored it. I don't know. But obviously his instructor must have completely ignored it as well. He wasn't in my trig class. I'm not teaching it this term. He was supposed to be in my trig class. So if I sound like I'm getting obnoxious with it, I probably am, because I want you to know they're out there. It's there for your benefit. Please use it. So this example is there. Okay. And here is the A part. Here's a sequence. A sub n. Set of numbers. That's what the curly brackets is. Hey, we've seen this one before, haven't we? 3 plus a negative 1 to the nth.
This was the 2, 4.
That's your 2, 4, 2, 4, 2, 2, 4, 2, 4, 2, 4, 2, 4. I can't write. 2, 4, 2, 4. Blah, 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 and dot, dot, dot. Okay? Now, do you think that converges or diverges? Yes. And diverges doesn't mean they get further apart. That's sort of what it sounds like. It isn't. It means it doesn't converge. And this certainly doesn't converge. You can pick an epsilon, even as large as 1, okay? And if you say, let's do a half. Epsilon equal a half. And let's just say we wanted it to converge to 3. That's in between 2 and 4, right? Does this converge to 3? Well, I'll pick an epsilon of 1/2. Can you find anything here that between 3.5 and 2.5, that's epsilon, or L plus epsilon and L minus epsilon, 3.5 to 1.5, none of these fit in there. Not at all. So this does not converge. That means it diverges. Even though they're not getting further apart, that's beside the point. Divergent means it doesn't converge. Okay. Now, pretty interesting. They're doing A's with A's and B's with B's. I mean, you don't have to number them this way. B sub n. And this was the one I think we also did, n over 1 minus 2n. Okay. No, I don't think we did this one, did we? A, I know we did. Yeah, we did. There was the B one before. Okay? Now, okay. We listed them before. Let's this time use our function notation. Okay? And what would that give us? Right? Yeah, that's what we say, alpha n equal that. How do we evaluate that? Anyone have an idea? It's a nice little trick that works pretty frequently. It's multiplied by 1. That should work, shouldn't it? That shouldn't change anything, should it? But the form of 1 is going to be 1 over n over 1 over n. Now remember, n's not 0. N's always greater than 1, right? Some positive integer. Well, what happens here? What's your numerator become? Isn't this thing right here 1? And multiplying by 1 won't change its value any, will it? No. Okay. So what's your numerator become? What's that again? It's n over n, right? 1. Okay. I couldn't hear what you said. Okay. Your denominator becomes 1 over n, right? Minus 2 over n, right? Okay.
Maybe that 2 over n.
No, I mean 2. I'm sorry, minus 2. Sorry. You're absolutely right. I was thinking this isn't coming out right. Okay. Now, what is 1 over n as n gets very, 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 very large? That's going closer to 0. So this is minus 1/2. Right? Now, remember what we said that one was? We did minus 1, minus 2/3, minus 3/5, minus 7/4, minus 5/9, minus 6/11. I said that's getting closer and closer to minus 1/2. That's it. There's a nice little trick to do. Okay. So that's example 3. Let's move to example 4. Any questions on 3?
How would you check that using the epsilon?
Say that again.
Is there a way to do it using the epsilon?
Probably, but I sure don't want to.
No.
If I can figure out a way around the epsilons, I do. Yeah, but this shows it, yeah. Yeah, you can tell a math major. He's wanting to see that proof, yeah. Go for it. Okay. You would do almost the same type thing here. But, okay, let me erase all this. Yeah, we got a little bit of, ooh, not a lot of time. What is it? About 5 minutes?
Yeah, 6 minutes.
6 minutes. Let's see if we can get example 4 done. Show that the sequence whose nth term is a sub n, and this is equal to n squared over 2 to the n minus 1. Show that that converges. Now, this I'm pretty sure was our example C from before, wasn't it? I believe so. Okay? Now, again, let's go to the function. F, they go to x. Sometimes they do x's, sometimes they do n's. So let's make this as x squared over 2 to the x minus 1. Okay? And we want to see if this has a limit as x is approaching infinity, right? Of x squared over 2 to the x minus 1. What's x squared doing as x goes to infinity? Going to infinity even faster, right? It's really going to infinity. But what's 2 to the x minus 1 doing as x is going to infinity? It's going very, very rapidly to infinity. So this is an infinity over infinity case. Do you remember what rule we use for those kind of things? Hint.
The largest exponent.
The what?
We use the largest exponent.
Okay. This, actually, you're right on the money there. I don't know whether you realize it or not. Because as this goes to infinity, that's much bigger than that. So you're really pretty close to right on the money. But what rule? Infinity over infinity is not that dissimilar from 0 over 0. What rule do we use to determine if a 0 over 0 has a limit? If you can't plug it in, do, almost seems like a hospital, doesn't it? L'Hopital. Remember that? L'Hopital's rule? Oh boy. Okay. Now, L'Hopital, just a little bit of background here, was a very good mathematician, I'm sure. He studied under one of the Bernoullis. I don't remember which one. There were so many really great Bernoullis. Okay? He studied under one of them. Johann, maybe, I don't know, one of them. Jacob, I don't know. Okay? But he learned an awful lot from him. But one thing that L'Hopital did, he went lots of places and learned lots of things, and he decided to write a textbook. I don't think the Bernoullis ever bothered to stop and write textbooks, but he wanted to write a textbook so everybody, and he did it. And in his textbook, he acknowledged he got this from one of the Bernoullis, whichever one he learned it from. But guess what? Everybody refers to it as his rule, not Bernoulli's rule. And boy, did that Bernoulli get upset. But he said, look, I referenced you. I said it came from you, but everybody calls it L'Hopital's rule. What does L'Hopital's rule say? Take the derivative of the numerator, which would be 2x, and the derivative of the denominator. Oh, this one is a little tougher. Anyone remember what derivative of 2 to the x is?
It's a chain rule.
What's that?
It's a chain rule, isn't it?
Yeah, sort of, a little bit. Okay. It would be 2 to the x over log 2. I think that's right. Go back and check. Derivative of, I don't see it in that table, so I think you have to go to the back of the book. I don't sit back here either. Yeah. Does anyone find it?
You take your word for it.
Okay. Oh, wait. I'm looking on the integrals. I'm looking on the... They don't have a derivative table back here. Okay, I know in the text you can find it. I want to show it to you so you'll know where to find it if you ever need it. It's in chapter 5. I think it's 5.4 or 5.5 perhaps. Let's see. We're running out of time, aren't we? What's that?
I don't know which Bernoulli it was, but I know it wasn't Daniel.
It wasn't Daniel. It was one of the older brothers. Okay? Jacob or Johann, one of those two. Here it says, find the derivative if you go to page 354, chapter 5, section 5.5. It says, differentiate functions to other bases, y equal 2 to the x, which is exactly what we've got here. And that is... Oh, it's multiplied, not divided. Sorry. 2 to the x times log 2. I was integrating, not dividing. Okay. Not differentiate. Log 2 times 2 to the x. Okay. Now this is 2x up here. This is 2 to the x here. Take the limit as x goes to infinity. Still going to infinity, right? Do it again. Derivative of the numerator is 2. Derivative of the denominator is log 2 squared. 2 to the x, okay? Numerators as x goes to infinity is 2. Denominator, infinity. 2 over infinity is? Second? 0. So this limit is 0. Okay? Oh, there they had it in the book. I didn't even look. Okay? Yeah. And because f of n equal a sub n for every positive n, you can conclude this also converges to 0. All right, I think we have run out of time, big time, haven't we? Okay, we'll pick up next time with the next slide, which is, let me get back to it so when I, oops, that's it right there. That's where we'll begin next time. I need to find my pencil and my eraser. Okay. All right. We'll begin there next time. Did we get enough that you can do some homework exercises? I hate to send you home with no homework exercises. Yes, we can do any of the odds 5 through 9. They're all at Calc Chat. 9's at Calc View. You can do 11. It's at Calc Chat. And I would do all 4 of 13 through 16. Only 13 and 15 have answers in the back and at Calc Chat, but you should be able to do all 4 of those. And stop there because we'll pick up from there next time. Okay? Good deal. All right. See you Wednesday. Oh, and by the way, let me say this too before I forget it. As far as I know, I'm going to be out of town this Friday. So if you were planning to come to the Birmingham campus to catch me, I'm not going to be there. I'm requesting leave for this Friday.